All right, back to chapter 2. We talked about density a little bit. That shows up in this chapter, but we're going to start it from the top. What is matter? Matter is anything that occupies space and has mass. Some types of matter, like chairs, tables, people, are easily visible. Other types of matter are impossible to see without magnification. Like germs, maybe, air particles, etc. You, notably, occupy space and have mass. You matter. Or you are matter. You consist of matter. It's fun, it's corny. So that's matter. Matter can, often does, appear smooth and continuous, but if you zoom in far enough, it's actually not continuous. And it's often not even smooth. Matter is composed of atoms, which we can sort of think of as tiny building blocks. They are about 100,000 times thinner than human hair. So you can stack 100,000 of them across the width of a single human hair to give you an idea of roughly how small they are. And they are the fundamental building block of matter. If you are familiar with Lego, right, the tiniest little Lego piece, that's kind of what our atoms are. And we can build other things out of them. We can bond atoms together to form molecules. So a molecule is just a group of two or more atoms that are linked together. And they often have a specific arrangement. And if you change the arrangement, it's no longer the same molecule, it's a different molecule. So the order is important. Ultimately, all matter is composed of atoms. In some substances, not all substances, but like metals, a lot of metals, the atoms exist as independent particles. This isn't a picture of independent particles. It's a bunch of metal spheres, I think, that are all linked together. And that would kind of be how atoms would sit in a metal. So like if you just got a copper pipe or something, the atoms are all kind of just sitting next to each other like that. That's different than in a molecule. In a molecule, they're actually like linked together. There's like a sticky goop you could think of sticking them together. Whereas in a metal, you can separate them apart more easily. In other things, we get chemical bonds that connect our atoms and produce something called a molecule. This is an example of a modeling kit where we've got each of these different balls, these orbs, representing a different atom. So the black ones are representing carbons. We've got whites that are representing hydrogens, blue for nitrogen, red for oxygen. You don't need to have those colors memorized, but that's what we're seeing here. And the little gray things between them are bonds. And if you were to get some of whatever this substance is, I forget what it is, and you separated it out, you cut it up, chopped it up into tiny little pieces, it would always break off in these. They wouldn't separate these bonds unless you put in a lot of energy, like if you burned it. We can classify matter based on its physical state, the way that the atoms and molecules are arranged. Some of this will be review, hopefully. So our common states of matter, the three that we care about the most for this class, are solids, liquids, and gases. You can probably see in our solids, they're very well arranged. Not always the case. They're all just sitting right next to each other. In our liquid, B here, this is liquid oxygen. The orientation of these oxygen molecules kind of changes. It's not nice and neatly arranged. And then in C, this is oxygen gas, like we're breathing in. They're completely separated and moving independently of each other. So first up, the solid state. In our solid state, the atoms and molecules are packed close to each other, touchingly close, as I will often call it, and in fixed locations. Not moving past each other. This isn't to say that they're not moving, but the movements that they're making are just like vibrating around, oscillating in their place. It's sort of like when you're sitting in here during lecture. You can still move around, you can write stuff, you can bump your neighbor with your elbow or make a joke, right? But you're generally not going to be swapping places with other people in the room. That's sort of our solid state. The other analogy that I like for solid state is at a movie theater. You get to a movie theater, you hop in your seat during the movie, you can move around, you can eat popcorn, you can whisper to your neighbor, you can kick your feet, you can whatever you want, but you're not getting up and moving past each other and swapping seats with people for the most part. And that's kind of our solid state. So like students in lecture, or people at a movie. And solids, because they're touchingly close, you can't pack them in any tighter. So they have a fixed volume. You can't push them any closer. They're already as close as they're going to get. And they also have a rigid shape because they're not moving past each other. The molecules or the atoms are not moving past each other. So we get a rigid shape. We've got two types of solids, broadly speaking. We've got crystalline solids that form crystals, and they have long-range repeating order. So there's a repeating pattern to the shape that they make. The way that I think of this, if you take a picture, if you were to zoom in on the material and you took a picture of one spot on that material and you scrolled over however long you wanted to go, if you scrolled and looked at some other part, does it look exactly the same? Could you get those two images to overlap? This would be like a really boring housing development where all the houses are exactly the same. You take a picture of one part of the neighborhood, you could go to another part of the neighborhood and find basically the exact same picture. That would be a crystalline solid. Quartz and other fun-looking gems, diamonds, emeralds, beryls, are all examples of crystalline solids. Quartz is a silicon oxide, so it's silicon and oxygen. There's also an amorphous form of the same thing, which is glass. So glass is an amorphous solid. It doesn't have long-range order. You can still see through it. But if you were to zoom in on a section of, thing of glass here on the bottom right, and you tried to overlay it with another section of the glass, you would have a harder time getting it to match up. Whereas the quartz, you could pull a spot, and you would pretty easily be able to see how it overlaps with another section of the image. in our liquid state, our atoms and molecules are still close to each other, touchingly close. They're still close enough that they can interact with their neighbors, but the thing that's changed is now they can move past each other. And because of that being touchingly close, they still have a fixed volume. So you can't compress liquids, at least not very much, because they're in close contact, but they will assume the shape. They'll run, they'll flow, because they can move past their neighbors. So what I like to think of for a liquid state is people up at the very front of a concert, assuming it's not like an orchestral performance or a symphony hall, or a musical or something, but like if you're at a rock concert or a pop concert, the people up in the very front are all probably packed in about as tight as they can possibly get with each other. They're all touchingly close, maybe more than they'd like to be, but you're not stuck in your spot the same way you're stuck at a movie theater. If you have to get up and go to the bathroom, you can slip your way past the crowd and get back to the bathroom, and you can fight your way back to be up at the front with your friends. Somebody might try to squeeze past you into the front to get a better view or to get a picture. You'll be moving around each other. If there's a mosh pit, there might be a little bit of space, but there's movement. It's not all fixed and stuck in place. So that's our liquid state. Our last state is the gas state. So in the gas state, we've got atoms or molecules or other particles that are separated by large distances. So we have empty space between our atoms or our molecules or whatever else they might be. And they are also able to move relative to each other. But the big change is that we've now introduced this empty space. And since we finally have some empty space in there, we could compress the gas. So this very low quality rendering of a piston. On the left, our piston is up high, and we've got all of our particles in there. We can push the piston down, and that'll force our particles to get a little bit closer to each other. We've just removed some of that empty space. So they're a little less free to move around. So our gases are compressible because of that empty space. And assume the shape of their container. Since they're not clumped up together like a liquid, they can also move up, unlike liquids. Like if you spill milk, right, it's just going to stay on the floor unless you're in space. It's not going to be distributing itself all the way around the kitchen or the classroom or wherever you're spilling your milk. And for this, I sort of think of like when we have events out on the green, right? There's a lot of people all milling around. There's lots of space in between people. Usually people don't just clump up as tight as they can with strangers or friends. There's lots of empty space between people. You're all moving around freely to see what you want to see. And then somebody might call everyone in, and we're going to do this thing together. And then you can bring everyone closer to each other to talk about whatever thing they're talking about. Giving away prizes or something, right? You can compress everyone down. You'll still be moving past each other. So those are some basic properties. Here's a table with those characteristics, with those properties on it as well. If you're interested in hydraulic presses, the reason that hydraulic presses use liquids is because the volume is definite. They're already touchingly close, but the shape is indefinite, so they can flow past each other. That means that you can push on a large area, like a large surface area of the liquid, apply a low pressure there, focus pressure down into a small part, and that's how you get hydraulic presses. You wouldn't be able to do that with a solid because they don't flow, and you also can't do it with gases because you would end up compressing your gas probably down into a liquid, and then you might as well have just started with a liquid. So there's some sort of unrelated flavor text for you. We can also classify matter based on its composition, what its pieces are, its smallest pieces, what sort of atoms and molecules it's made out of. And we've got two classes of things. We've got a pure substance. As the pure part implies, it's just one thing. So we've got only one substance. There's nothing else mixed in there. And then we've got the very aptly named mixture, which is two or more substances. With whatever proportions you might want. So water would be an example of a pure substance. Lemonade would be an example of a mixture. You've got the lemon juice plus all the stuff that's in the lemon juice. You've hopefully got some sugar, and you've got water. You've got a mixture. And you can make lemonade that's very sweet. It's got a lot of sugar. It doesn't have very much lemon juice. You can make it with a lot of lemon juice, how I like it, and not as much sugar. There's lots of different recipes, ways you can make lemon juice. You can use different types of lemons. It's still what we would call lemonade, right? It's a mixture. So that's like our broadest way of categorizing things. Is it a pure substance or is it a mixture? And we can further break those down, pure substances and mixtures, into elements, compounds, and homogeneous or heterogeneous for mixtures. And we'll be talking about each of these. So for elements are in the pure substances category, and they can't be broken down into simpler substances. There are 118 elements on the periodic table. Like the one that we have in class. They are actually all named. The periodic table we have in the class is just a little bit old. So our elements, all our different types of elements, all 118 options are listed out on our periodic table. And that's the very simplest, at least for now, that we can break things down. We also have compounds and mixtures. So a compound, a pure substance, can be a compound, and that's two or more elements that are in fixed definite proportions. An example would be water, which has the chemical formula H2O, which means that we've got two hydrogens and one oxygen. And water, you can actually break down into simpler substances. You can break the hydrogens and the oxygens apart from each other. One of the ways you can do that is running electricity through water, and you can actually separate out the hydrogen and the oxygen. Don't try it at home because it's electricity, and also hydrogen and oxygen gas are explosive. Very flammable. As you might imagine, we've got 118 options for elements. Several of those don't exist right now in any meaningful amount. When you can mix different elements together, there's lots of ways that you can mix elements together. So compounds are actually much more common than just finding pure elements. And if you don't have a pure substance, that means you've got a mixture. And a mixture is going to be composed of two or more substances, either elements or compounds that are just in the same vicinity. They're not chemically bonded to each other. You just lumped them all together. It's like balls in a ball pit. There's children in there. There's balls in there. It's a mixture of children and play place balls and vomit and other things, probably. Horrible things, ball pits. But you can separate them out. You can pull all the children out of the ball pit. You can pull all the balls out of the ball pit. You can pull all the detritus and debris out of the ball pit. They're just mixed together. You don't have to go in with electricity and separate children that have fused to the ball pit balls. So you can separate them out, and the proportions also can vary. Sugar water would be an example of a mixture. You've mixed sugar and water, and there's some other stuff in there as well. Other examples of mixtures: salt water, and water and sand. The way that you would separate these out varies, but you can separate them out. Desalination plants do the energy exhaustive job of separating salt and water, and separating water and sand is relatively easy. Just pour the water off. And those are two types of mixtures, One of them is homogeneous. And these are either the same consistency or different consistency throughout. So a homogeneous mixture is going to be something where if you, like for lemonade, if you take a sip from one part of the lemonade and a sip from a different part of the lemonade, as long as it's well mixed, you should get the same taste of the lemonade. You're not going to got to make sure I get from the best part of the lemonade, pitcher or whatever, right? Bronze, steel, air, sodas, all kind of the same idea. If you're pulling from one part of it, you're getting the same thing as if you pulled from a different part. So you're getting the same ratio of the components no matter where you pull it from. Milk is also homogenized so that you don't have the creamy, frothy milk fat sitting at the top. A heterogeneous mixture has a different consistency throughout. So you're going to get a different ratio throughout. It might also separate out. So marble countertops, soups, stews, as long as you didn't blend them. Soups and stews are going to be a heterogeneous mixture, like chicken noodle soup. When you eat chicken noodle soup, some mouthfuls are going to have lots of chicken, some won't have any chicken, some will have lots of noodles, some will have no noodles. Unless you blend it up in a blender, which would be disgusting, that's going to be your experience with chicken noodle soup. And that's an example of a heterogeneous mixture. It's a different flavor, slightly different mouthful every single bite, And vinaigrette salad dressings, similar idea. If you don't shake them up before you use them, you might have a very oily salad dressing when you go to use it. All right, each of these is a type of matter. Identify them as a compound, an element, a heterogeneous mixture, or a homogeneous mixture. We've got a stuffed animal shark, coffee, alcohol like in an older thermometer, an analog thermometer, and selenium. Take a moment, think about them, see if you can figure out what each of these is. Maybe compare notes with your neighbor. All right, a stuffed animal shark, like any other stuffed animal, just chosen a shark in this example. It's a stuffed animal. Is it a pure substance? Is it made of just one thing? No, it's not, right? It's got a mixture of things. There's the fluffy insides as well as the fabric stitched outside. So it's going to be a mixture. Is it the same consistency throughout? If you chop off one part of a stuffed animal, is it going to be the same as if you chopped off another part of a stuffed animal? Probably not, right? You might get some of the outside fabric. You might pull from just the inside and then it's just cotton fluff. So that would be a heterogeneous mixture. It's not the same smooth consistency throughout. Coffee. Is coffee a pure substance or a mixture? To me, it feels like a pure substance, but it is actually a mixture. We're talking about brewed coffee, not the beans. So my coffee in my mug, it's a mixture. There's more than just one thing in there. There's some water, there's electrolytes, there's caffeine. There's other good stuff in there. If you have a pot of coffee and you pour 1 cup for somebody else and you pour 1 cup for yourself, are you getting the same coffee? Yeah, you're getting the same coffee. It's well mixed. That's a homogeneous mixture. Thermometers often use alcohol, modern thermometers at least. There's usually some dye or coloring in there with them, but just thinking about the alcohol in the thermometer, do we think that's a pure substance or a mixture? It would be a pure substance. On our periodic table, do we have alcohol? We don't have alcohol on our periodic table. That's going to be a compound. How about selenium? Is selenium a pure substance or a mixture? Selenium is also a pure substance. Is selenium on our periodic table? It sure is. Se is selenium. So that means it's an element. Questions about any of those for classifying matter? All right, so in review, matter can either be a pure substance or a mixture. If it's a pure substance, it's either an element, we can find it on the periodic table, or it's a compound. It's a mixture, chemically combined elements from the periodic table. If it's a mixture, it can either be the same smooth consistency throughout, or it can be sort of chunky, heterogeneous, different consistency throughout. Our mixtures can be a mix of elements, it can be a mix of compounds, or it can be a mix of both. So we could have elements mixed with compounds. One way that we can distinguish our different substances, because there's lots of substances in the world, and how would we tell them apart if not for their properties? So physical properties and chemical properties are some way that we can determine if two things are the same or if they're different. Physical properties are things that are displayed that don't change the identity. So it's the same chemical or substance before and after. Like gasoline. If you smell gasoline, is it still gasoline? It sure is. It sure is still gasoline, and it smells great. Don't smell it too much, though. It's bad for you. If you taste something, you can argue that that's maybe a little bit of a change of the properties or a change of the substance. But it's roughly the same thing before and after you tasted it. You taste the sugar. It's still sugar when it goes into your body. It hasn't magically become something else. Color, if we observe the white shirt that I'm wearing and we say, oh, that's a white shirt with blue dots on it, it's still a white shirt with blue dots on it, right? It hasn't changed. A red shirt doesn't change color because you've observed that it's red. And other things like the melting point and the density are also things that we can observe without changing the chemical. Chemical properties, on the other hand, chemical properties are only observed through change. So when you burn your gasoline, hopefully in a car engine and not just like out in a field, when you're burning gasoline, you can't just route the exhaust in your car back into your gas tank to burn it again, right? Because it's not gasoline anymore. It's turned into carbon dioxide and water and some other stuff that hopefully your car engine or your carburetor or whatever cleans out. But it's changed into other stuff. After burning, it's no longer gasoline. Other things like corrosiveness, acidity, toxicity, those also oftentimes are only displayed through changing identity. So for physical properties, melting point and other phase changes, like boiling or evaporation, condensation, freezing, those are physical properties. When you melt some ice and it turns into water, it's still water. It was water when it was ice, and it's water when it's liquid water. Both are forms of water. Our beloved H2O. All that's changed is the way that the molecules are related to each other. Candle wax burns. That's the part that keeps your flames burning long time in your candles. There is a physical change involved. The heat from the flame melts the wax, and it wicks up the wick, and then it burns to produce the flame, and then it turns into other stuff. So probably some carbon dioxide, water, and other stuff. That other stuff is what produces soot, for example. Determine whether each of these is a physical or chemical property. Is it the same thing before and after we observe this thing or it does this thing, or does it change? That would be physical and chemical properties, respectively. Hydrogen gas is explosive. The explosiveness of hydrogen gas, is that a physical property? Is it the same thing before and after it explodes, or is it a new thing after it explodes? What do we think? Yeah, it's a new thing. The explosiveness of hydrogen gas. It turns into something new or something else, probably water. So that would be a chemical property of hydrogen gas. The bronzy color of copper, that brown color that you see on copper pipes, copper wiring, is that a chemical property? Does it change when you observe that? Or is it a physical property? Does it not change? It's a physical property. It's still the same color after you observed it. It's still copper. What about the shiny appearance of silver? That one's also a physical property. And this last one, dry ice, do a thing called sublimation, where it changes from a solid directly into a gas. Do we think that that is a physical or chemical property? Dry ice is solid carbon dioxide. When it sublimes, it turns into also carbon dioxide. And sublimation is a phase change. It's just one that you may not have heard of. So this is also a physical property. Ice in your freezer can also sublime, and we'll talk about that more in a future chapter. Questions about physical chemical properties? All right, we're having a good time. Going along with physical and chemical properties, we have physical and chemical changes. It's the same ideas here. So for a physical change, it's the same chemical before and after. So it might look different. The atoms and molecules might be arranged differently, like when ice melts. Ice is solid water, and so the water molecules are just packed in tightly next to each other. They're touchingly close, and they're in a fixed arrangement, kind of like people at a movie theater. When we melt it, it's still water, but we've given them a little bit of energy, and so the water molecules can move around and past each other. But it's still water. In a chemical change, the matter does change its composition. a new chemical or chemicals are formed. So it's becoming something else. For example, the Statue of Liberty used to be, well, it's copper, so it used to be brown, and now it's green. It's reacted with gases in the air and salt water and stuff to form new compounds. In this example, the color change indicates a chemical change. So our physical changes, our most common physical change is a state or phase change. Anytime that we're changing between the different states of matter. Solids, liquids, gases, and even solids and gases. And we've got names for those changes. But regardless of what form it is, it's still the same substance. Phase or state changes are always physical changes. And let's box that in for no particular reason. I'm joking, there's a particular reason it's important. So that's one of our more common phase changes, or physical changes, rather. In our chemical changes, we are changing the identity of the substance, and it results in something new. Matter undergoes a chemical change when it goes through a chemical reaction. We're going to be looking at a lot of chemical reactions in this class. And our general setup for a chemical reaction is that we have reactants on the left side. Can anyone guess what reactants do?
They make reactions.
They react and make reactions. They combine together, they work with themselves, and they blow up into other things. So we'll always be writing our reactants on the left side. We'll have an arrow. Oftentimes it'll just be a one-way arrow. Sometimes it'll be a double-headed arrow. The arrow represents a chemical change. Something's happening. We won't go into the details necessarily of what's happening. And it goes on to produce the aptly named products. I will often say left side, right side, reactants, products. I'll use those terms sort of interchangeably. Left side's reactants, right side is products. And you can have one reactant and one product. You can have two reactants, two products, any mixture of numbers of reactants and products. Any questions so far? All right, so other examples of physical changes. The big one, changing between states of matter, solid, liquid, gas. Separation of a mixture, like sand and water. That would also be a physical change. They were sand and water when they were combined. You separated them out. Now it's sand by itself and water by itself. They're the same chemicals. Nothing crazy happened. And physical deformations. So cutting, denting, stretching, making things into wire. It's the same chemical that you had before. You're just changing the way that it's arranged, the form of it. Making ice sculptures. It's still water, just prettier. Also making solutions, which are types of mixtures like sugar water. Or simple syrup, as it might be called. Some of these are physical changes. Other ones, like with table salt and other ionic compounds, which we'll learn about later, some of those are not physical changes and are in fact chemical changes. Oddly specific example, perhaps. Was it on the pre-lab? Maybe it was. Some signs of chemical changes include temperature change can sometimes be a sign of a chemical change, or like instant ice packs. There's a reaction going on that's causing the temperature change. The light produced by glow sticks is an example of a chemical change. Color changes, like copper turning green. Bubbles or gas being formed, like with baking soda and vinegar, which is the classic, volcano science experiment. If there's a change in the smell of the chemicals or in the taste of the chemicals, and if you combine two clear liquids to form a solid, that would also be a sign of a chemical change. These will be important for our lab this week, the chemical changes and physical changes. All right, let's try to classify each of these as a physical or chemical change. We've got A, boiling water.
Physical.
Boiling water is a physical change. Why is it a physical change?
Because you're not breaking down, you're not changing the chemical, you're just changing the state.
Yeah, it's still water. It's just a phase, change. It's just a phase change. A nail rusting, like one that you'd use for construction, not your fingernails. That's going to be a chemical change. Rust is a video game. It's also a different chemical. If we mix a green solution and a colorless solution, and the resulting mixture has a pale green color, do we think that's a physical or chemical change? We've got guesses for physical. Why is it a physical change?
Because you're not chemically changing anything, you're just mixing the two colors.
Yeah, we've just diluted our green liquid. We've watered it down, so to speak. How about if we mix two colorless solutions and the resulting mixture has a yellow solid that forms at the bottom? Would that be physical or chemical? that would be chemical. A new compound has formed. The new compound being the yellow solid. Right, we didn't have a yellow solid to begin with. We had two clear liquids. We mixed them together and something new came out of them. That yellow solid would be a new chemical. All right, last slide for today. You can separate mixtures with physical changes. This is often how essential oils are made, or one way that essential oils can be prepared. In this example, we've got salt water. So you can heat up this salt water. That causes the water to evaporate. We've got a temperature up in the neck above here just to monitor the temperature that we're at. Sometimes the temperature matters. And it's stopped at the top as well. Please wait to pack up. And then we've got this condenser flask. The condenser has cooled water that's running in. And this is a place for our water to condense. And then it drips down into our receiving flask. So this is how a desalination plant might work. A weird example of it. If you put catnip or orange peel or something into this saltwater flask, the distilling flask, you would instead get out catnip essential oil, which is very potent for cats, or you would get out an orange essential oil. A lab that you might do in the future, depending on where you go. Question?
Does this sheet get passed around?
The attendance sheet should be going around. Let's just make sure it's in the back. Let's just make sure that we get that for everyone to sign. Okay, that'll do it for today.